Hello there, and welcome to the Sleep with Science channel, where tonight we are going to drift together into one of the most quietly profound mysteries that has ever settled itself into the human mind. A question so vast, so gently haunting, that simply holding it in your thoughts has a way of dissolving everything small and ordinary about the day you just lived through. So let your body grow heavy now. Let your shoulders release whatever they have been carrying. Let your breath find its own slow, unhurried rhythm, because where we are going tonight requires nothing from you except stillness and wonder and the willingness to float. Somewhere above you, beyond the ceiling, beyond the atmosphere, beyond the cold and silent threshold where Earth's air finally surrenders to the infinite dark, the universe is doing what it has always done. It is simply existing, enormous beyond any number your waking mind could comfortably hold, ancient beyond anything your memory could trace, and filled, so unimaginably filled, with the raw materials of possibility. Stars are being born in slow, luminous clouds of hydrogen gas that stretch across distances so great that light itself, traveling at 186,000 miles every single second, would take hundreds of years just to cross them. Other stars, having lived their long and brilliant lives, are collapsing quietly into the dark, or erupting outward in final, spectacular releases of energy that seed surrounding space with carbon, with iron, with oxygen, with the very atoms that make up the hand resting on your chest right now as you breathe. The universe is approximately 13.8 billion years old. That number tends to pass through most of us without truly landing, so let it settle gently for a moment. 13.8 billion years. Our own sun, that warm and steady presence that has governed every morning of every human life that has ever been lived, is only about 4.6 billion years old. Which means that before our sun had even formed, before the solar system existed in any recognizable sense, the universe had already been running its extraordinary experiment with matter and energy and time for more than 9 billion years. 9 billion years of stars forming and dying. 9 billion years of galaxies assembling themselves through gravity and dark matter into those enormous, slow-turning spirals and ellipses scattered across the deep field of space. 9 billion years during which the basic chemistry of life, carbon bonds, liquid water, atmospheric pressure, had already been made possible in countless locations, long before a single human ancestor had drawn a single breath on a small blue world in one unremarkable corner of the Milky Way. And yet, tonight, if you were to step outside and look up at a sky dark enough to see the stars in their full ancient abundance, you would see no signal. You would hear no transmission. You would find no undeniable, universally agreed upon evidence that anything else out there has ever looked back. The silence of the cosmos, in the face of its overwhelming scale and age and chemical richness, is one of the deepest and most beautifully unsettling things our species has ever had to sit with. This is not a new tension. Thinkers have wrestled with it for centuries, though only in the last several decades have we developed the instruments and the mathematical frameworks to truly measure the weight of the question. In 1950, a physicist named Enrico Fermi sat down to lunch with colleagues at Los Alamos and, during a conversation about interstellar travel, reportedly asked something devastatingly simple, something so clean and so direct that it has echoed through scientific thought ever since. He looked at the numbers. He considered the age of the galaxy, the abundance of stars, the reasonable probability of other worlds, and he asked, in essence, where is everybody? We call it the Fermi paradox now, and over the decades, brilliant minds have offered dozens of answers. Perhaps intelligent life is extraordinarily rare, a vanishingly unlikely accident of chemistry and time. Perhaps civilizations tend to destroy themselves before they can reach outward. Perhaps the distances involved are simply too immense for any signal or vessel to bridge within the time frames that matter. Perhaps we have been listening on the wrong frequencies, or looking in the wrong directions, or operating with instruments too crude to detect what has always been there. Or perhaps, and this is the possibility that tends to arrive quietly, in the dark, in the space between waking and dreaming, perhaps there is something else. Something more fundamental. A kind of barrier, not built by any civilization, not imposed by any force we have yet named, but woven into the very structure of existence itself. A threshold that separates the universe's potential for life from life's ability to reach across the void and find another. A hidden wall, built not from stone or steel or any material a human hand could touch, but from the quiet, indifferent mathematics of the cosmos itself. Let that thought rest in you for a moment. Don't try to solve it. Don't try to rush toward any answer. Simply feel the shape of it, the way it opens something wide and cathedral-like inside the chest, the way it makes the ordinary sounds of your home, the settling of walls, the soft movement of air through a vent, the distant murmur of a world still turning outside your window, feel somehow both smaller and more precious at the same time. That is what genuine mystery does. It doesn't frighten so much as it reorients. It reminds you that existence is not a solved equation. It is something far more beautiful than that. The observable universe, the portion of all that exists that we can theoretically detect from our position in space, spans roughly 93 billion light-years in diameter. Pause with that number. Not 93 billion miles, which would itself be incomprehensible. 93 billion light-years. A single light-year is approximately 5.88 trillion miles. The distance from Earth to our nearest stellar neighbor, Proxima Centauri, is about 4.24 light-years, meaning that a spacecraft traveling at the speed of our fastest current probes would require tens of thousands of years just to reach the closest star to our own Sunday. And Proxima Centauri is, in the grand architecture of the cosmos, essentially our next-door neighbor. It sits in the same quiet suburban arm of a galaxy that itself contains somewhere between 200 and 400 billion stars, and that galaxy is just one of an estimated 2 trillion galaxies scattered across the observable universe. 2 trillion galaxies. Each one a vast, slowly rotating collection of hundreds of billions of stars. Each star a sun, many of them orbited by worlds, and many of those worlds sitting at the kind of distance from their host star where liquid water, that extraordinary, humble, life-enabling molecule, could theoretically pool and gather and persist across geological timescales. When astronomers began discovering exoplanets in earnest in the 1990s, when the data started flowing in from missions like Kepler and later TESS, what emerged was not a picture of cosmic rarity but one of cosmic abundance. Planets are not exceptions. Planets are the rule. Our galaxy alone is now estimated to contain more planets than it contains stars, which means the Milky Way is home to hundreds of billions of worlds, many of them rocky, many of them temperate, many of them sitting in that delicate zone of stellar warmth that scientists sometimes call the Goldilocks region, not too hot, not too cold, but sitting at just the right distance to hold the conditions that, here on Earth, gave rise to everything that has ever lived and breathed and wondered. And so the silence becomes stranger, more layered, more worthy of this slow, unhurried attention we are giving it together tonight, in the dark, in the quiet, with nothing pressing down on either of us except the soft weight of curiosity and the gentle pull of sleep beginning to gather at the edges of your awareness. You don't need to hold all of these numbers clearly. You don't need to map them or memorize them. Simply let them wash through you the way the sound of deep water washes through a dream, present, immersive, and larger than anything your waking mind would ordinarily allow itself to feel. Because here is where the mystery begins to deepen in the way that matters most for what we are exploring tonight. The universe has had time. Incomprehensible, almost offensive amounts of time. It has had chemistry, scattered with breathtaking generosity across every corner of existence. It has had energy in forms almost too varied to catalog. Stellar radiation, geothermal heat rising through the floors of ancient oceans, lightning crackling through primordial atmospheres rich with nitrogen and methane and ammonia. It has had the basic building blocks of complexity present since only a few 100 million years after the Big Bang, when the first generation of stars formed and began their nuclear burning and eventually, in dying, seeded the surrounding dark with everything the periodic table would one day require. Amino acids have been found in meteorites. Complex organic molecules have been detected in interstellar clouds. The ingredients are everywhere. They have always been everywhere. So then what stands between a universe this vast, this old, this generously stocked with everything that chemistry needs to begin its long experiment with complexity, and the emergence of voices that could reach across the dark and find each other? What is the nature of the gap between potential and presence? Between a cosmos that seems almost designed to permit life and the extraordinary, aching quiet that greets every instrument we have ever pointed at the sky? Some scientists speak of filters, evolutionary bottlenecks so severe, so improbable to pass through, that most lineages of complexity collapse before they can reach the threshold of awareness. Others speak of timescales so vast that even civilizations that have existed and reached and transmitted have long since fallen silent, their signals dispersed past any hope of detection across the deepening dark of an ever-expanding universe. Still others speak of something that sits not in biology, not in sociology, not in the lifespan of civilizations, but somewhere deeper, somewhere more fundamental, woven into the very fabric of how complexity arises from simplicity and how awareness emerges from matter that has, for billions of years, simply been doing what matter does, assembling, dissolving, reforming, drifting through the dark in patient, unwitnessed cycles that have no audience and no memory and no meaning until, one extraordinary day, they suddenly do. That transition, from matter that simply exists to matter that knows it exists, is perhaps the most quietly staggering threshold in all of nature. Think about what it actually represents. For billions of years, this planet turned. Oceans moved. Minerals dissolved and recrystallized in hydrothermal vents at the bottom of ancient seas. Simple molecules collided and broke apart and bonded again in slightly different configurations, following nothing more than the blind, elegant logic of chemistry and energy gradients. No one watched. No one recorded. No one felt the cold of those early oceans or marveled at the aurora-like electrical storms that swept across an atmosphere no human lung could have survived. The Earth was deeply, completely, and utterly alone with itself, a world in process, rich with activity, but untouched by the particular quality that changes everything. And then, somewhere in that ancient water, something crossed a line. A molecule learned to copy itself. Not intentionally. Not with any awareness of what it was doing or what it would eventually become. But a pattern emerged that could persist, that could replicate, that could carry information forward through time rather than simply dissolving back into the chemical noise from which it had briefly arisen. That first replicating molecule, whatever it was, wherever exactly it formed, in whatever warm and mineral-rich pocket of the early ocean it found its first foothold, was in some sense the most consequential event in the 4.5 billion-year history of this planet. Because everything that followed, every branching and blossoming of complexity across geological time, every organism that has ever drawn energy from sunlight or chemical gradients, every nervous system that has ever processed sensation, every mind that has ever turned its awareness upward toward the stars and asked a question about what might be out there, all of it traces back to that single, silent, unwitnessed moment when chemistry crossed the threshold into something we are still struggling to fully define. We call it life, but the word is almost too small for what it actually is. It is a process, a dynamic, self-sustaining, information-carrying process that has been running on this planet for somewhere between 3.5 and 4 billion years without interruption. Through mass extinctions and glaciations, through asteroid impacts and volcanic winters and the slow but relentless drift of continents across the face of a changing world, the thread of life has never once been broken. It has thinned to almost nothing at least 5 times in the geological record, events so catastrophic that the vast majority of species alive at the time vanished permanently, leaving behind only fossils and the chemical signatures of their passing in layers of ancient rock. And yet each time, from whatever small remnant of biological diversity survived, life expanded again. It diversified. It found new ecological niches, invented new metabolic strategies, reached into environments that would have seemed impossibly hostile to anything that had lived before. This resilience is part of what makes the silence of the universe so difficult to accept at face value. If life here has proven so tenacious, so inventive, so relentlessly capable of finding ways to persist through conditions that would seem designed to extinguish it, then why would we assume that the same chemistry, given the same ingredients and the same depth of time, would fail everywhere else? The assumption of cosmic biological uniqueness, the idea that Earth alone, among the hundreds of billions of potentially habitable worlds in our galaxy, managed to cross the threshold from chemistry to life, requires us to believe in a degree of cosmic coincidence so extreme that many scientists find it less plausible than almost any alternative explanation. And yet the sky remains quiet. The radio telescopes that have been listening, with increasing sensitivity and across widening bands of the electromagnetic spectrum, for the better part of 7 decades now, have returned from their long vigil with almost nothing that unambiguously speaks to intelligence beyond our own. There was one anomaly, a narrowband signal detected in August of 1977 by astronomer Jerry Emin using the Big Ear radio telescope at Ohio State University. He circled it on the printout in red pen and wrote a single word beside it that has defined the event ever since. Wow. The signal bore several of the characteristics that theoretical frameworks had suggested an intentional interstellar transmission might carry. It lasted 72 seconds, which was the full duration the telescope's observation window allowed. It has never been detected again. In the nearly 5 decades since that summer night in Ohio, no instrument, no observatory, no collaborative network of listening stations distributed across the planet has found anything comparable. The universe, on that one occasion, seemed briefly to lean toward us, and then withdrew back into its habitual, enormous silence. So we return to the question that rests at the heart of everything we are gently exploring tonight. As your breathing slows, as the weight of the day continues to lift away from your body, as the boundary between waking thought and the softer, more fluid territory of approaching sleep begins to grow pleasantly indistinct, we return to the barrier, the hidden threshold, the thing that stands, if something stands, between a universe so abundantly furnished with the conditions for life and the extraordinary fact of our apparent aloneness. That word, aloneness, carries a different weight when you hold it against the backdrop of 2 trillion galaxies. It isn't loneliness in the ordinary human sense, the kind that comes from a quiet evening or an unanswered message. It is something more philosophical, more structural, more woven into the architecture of what we are and where we find ourselves. It is the specific quality of being aware, of being capable of asking the question, while the question itself returns no echo from the dark. Let that settle across you like the gradual cooling of a room at night, gentle and all-encompassing, nothing to resist or resolve. Just the feeling of it. The particular texture of a mystery that is too large to hold completely but too beautiful to set aside. To begin to understand what the barrier might actually be, what its nature is, where it sits in the long chain of events that leads from a cloud of interstellar gas to a civilization capable of reaching outward, we need to walk very slowly through the steps of that chain. Not rushing, not skipping ahead. Because the answer, if there is one, lives somewhere in the details, in the quiet spaces between one stage of complexity and the next, in the transitions that seem straightforward when described in summary but reveal, upon closer inspection, a depth of improbability that is almost meditative in its profundity. The story begins, as so many cosmic stories do, with stars. Specifically, it begins with the fact that the universe was not always chemically rich enough to support the kind of complex molecular architecture that life requires. In the first moments after the Big Bang, the universe contained almost nothing except hydrogen and helium, with trace amounts of lithium scattered through the expanding, cooling plasma. That is all. The entire periodic table, every element heavier than lithium, every carbon atom in every organic molecule, every oxygen atom in every water molecule on every ocean-bearing world that has ever existed, had to be manufactured. And the universe has only one factory capable of that work. Stars are not simply sources of warmth and light. They are the universe's fundamental chemistry engines. Inside their cores, where pressures and temperatures reach conditions almost unimaginable from the comfortable distance of a habitable planet, hydrogen nuclei are forced together into helium, releasing the energy that makes stars shine. But the process does not stop there. As a star ages and its hydrogen supply in the core begins to deplete, the core contracts, temperatures rise further, and new fusion reactions become possible. Helium fuses into carbon. Carbon and helium combine to form oxygen. Heavier elements cascade from these reactions in a process of stellar nucleosynthesis that reads, when you trace it carefully, like the universe teaching itself chemistry one generation of stars at a time. The most massive stars, burning with a ferocious intensity that consumes their fuel in mere millions of years rather than the billions available to more modest stars like our Sun, eventually reach the end of their fusion capacity and collapse. The resulting supernova explosions are among the most energetic events in the known universe, brief, violent, luminous beyond easy description, and they serve a purpose that is almost poignant in its necessity. They scatter. All of that carefully assembled elemental richness, all of those carbon and oxygen and nitrogen and iron and calcium atoms built up through millions of years of stellar fusion, are thrown outward into the surrounding interstellar medium, where they mix with hydrogen and helium and the remnants of previous stellar generations and slowly, over millions more years, condense under the influence of gravity into new clouds, new protostars, new solar systems. Our Sun is what astronomers call a population 1 star, meaning it formed from material that had already been enriched by multiple previous generations of stellar birth, life, and death. The iron in your blood, the calcium in your bones, the oxygen in the air filling your lungs right now as you breathe slowly in the dark, all of it was forged in the nuclear furnaces of stars that lived and died before our Sun had even formed. You are, in the most literal and measurable sense, made of star material. Not metaphorically, not poetically, though it is undeniably that as well. Chemically, atomically, verifiably. The matter composing your body has a history that stretches back billions of years and spans distances across the galaxy that no human technology has yet traveled. This is one of the places where astronomical fact and the experience of wonder become genuinely indistinguishable from one another. And it is also, if you let yourself feel its full implication, one of the first places where the barrier begins to reveal itself in outline. Because the chemical enrichment of the universe, the process by which the cosmos became capable of hosting the molecular complexity that life requires, was not instantaneous. It took time. Enormous, slow, generational time. The first stars that formed after the Big Bang, those ancient, massive, metal-poor giants that burned brilliantly and briefly in a universe that had not yet learned to make anything heavier than lithium, could not have hosted life as we understand it. They lacked the ingredients. The universe had to live through multiple stellar generations before the raw materials of biology existed in sufficient abundance and distribution to make worlds like ours chemically possible. And this introduces a concept that will accompany us gently through much of what lies ahead tonight, settling into your awareness the way a soft sound settles into a quiet room, the concept of cosmic timing. Of the universe not merely needing the right ingredients, but needing to have reached the right moment in its own long development before the conditions for life could be met anywhere at all. Think of it this way, slowly, the way you might trace a finger across a fogged window on a cold night. The universe is approximately 13.8 billion years old. And for a very long time, for what we might call its early chapters, It was a place of remarkable violence and simplicity. Not simple in a peaceful sense. Simple in the sense of being chemically sparse. There were hydrogen atoms. There were helium atoms. There were trace quantities of lithium. And there was gravity, that ancient, patient, invisible hand that would eventually pull all of this sparse material into the first great fires. Those first stars, the ones astronomers call population 3 stars, a name that carries within it a quiet kind of grandeur, were unlike anything that exists in the universe today. They were enormous. Some of them may have been hundreds of times more massive than our own sun. They burned at temperatures so extreme that they radiated mostly in ultraviolet light, flooding their surrounding regions of the young universe with a fierce and sterilizing brilliance. And they lived fast, as massive stars always do, burning through their nuclear fuel in mere millions of years rather than billions, collapsing at last into supernovae of extraordinary power, or perhaps directly into black holes so massive they consumed themselves almost entirely before they could scatter their contents. But some of them did scatter. And what they scattered mattered more than almost anything else that has happened in the history of the cosmos. Because inside those first great stellar furnaces, the nuclear reactions that sustained them had been quietly, steadily building complexity. Hydrogen fusing into helium, helium fusing into carbon, carbon into oxygen, oxygen into neon, magnesium, silicon, sulfur, and finally, at the very end of the stellar sequence, iron, the element at which fusion can no longer release energy, the element that signals the star's final surrender. And when those first stars died and released their accumulated complexity into the surrounding gas, they were seeding the universe for the first time with the alphabet of chemistry. This is not a metaphor. This is what happened. The carbon in your body was forged inside a star. The oxygen you breathe. The iron in your blood. The calcium in your bones. All of it passed through the interior of a star that no longer exists, perhaps through several stars across several stellar generations, each one enriching the interstellar medium a little more, each one pushing the universe a little further along the slow road toward the chemical conditions that biology requires. And so the barrier begins to take on a temporal dimension. A dimension not just of space, of distance, of the vast and silent gulf between star systems, but of time itself, of epochs, of the universe needing to have lived through a certain number of chapters before the story of life could even begin to be written anywhere within it. Astronomers have modeled this process with increasing precision in recent decades, and what they find is both humbling and quietly beautiful. The peak of stellar formation in the universe, the cosmic noon, some researchers call it, occurred roughly 10 billion years ago. In that era, galaxies were forming stars at rates many times higher than they do today. The night sky, had there been eyes to see it, would have blazed with a density of new suns that our current universe, quieter and more aged, no longer produces at anything like that rate. The universe, in a very real sense, was busiest with the work of creation long before Earth existed. Long before our sun had ignited. Long before the solar nebula had even begun to collapse. Our sun formed approximately 4.6 billion years ago. It is what astronomers classify as a population 1 star, a third-generation star, formed from gas that had already been enriched by at least 2 previous cycles of stellar birth and death. It is, in the language of cosmic genealogy, the grandchild or great-grandchild of those original population 3 giants. And it is this lineage, this inherited chemical richness, that made the formation of rocky, chemically complex planets around it possible. That made the emergence of oceans and atmospheres and molecules of extraordinary intricacy possible. That made, eventually, us possible. But here is where the temporal dimension of the barrier becomes genuinely profound, becomes the kind of thought that you might want to let drift through your mind slowly as your body grows heavier against the surface beneath you. If the universe needed multiple stellar generations to produce the chemical conditions for life, and if those stellar generations each required millions to billions of years to complete their cycles, then there is an earliest possible moment in cosmic history before which life could not have existed anywhere. A threshold. A boundary in time as well as in space, behind which the universe had simply not yet done the preparatory work. And some researchers have attempted to estimate when that threshold might have been. When the universe first became, in principle, habitable. When the interstellar medium had been sufficiently enriched. When rocky planets could first have formed around sufficiently metal-rich stars. When liquid water could first have pooled on sufficiently stable surfaces under sufficiently gentle suns. The answers they arrive at are not discouraging, exactly, but they are humbling in a way that deepens the mystery rather than resolving it. Because what they suggest is that we may be living, cosmically speaking, not at the beginning of the era of life in the universe, and not at its middle, but somewhere in its early unfolding. In a universe that is, by some measures, only just beginning to produce the conditions under which minds can arise and look upward and ask the questions we are asking tonight. Hold that thought for a moment. Let it settle. You do not need to grasp it fully. You only need to feel the weight of it, the way you feel the weight of a blanket drawn slowly over you in a darkened room. The universe is not finished. It is still building. Still enriching, still seeding the interstellar medium with each new stellar death, each new supernova bloom expanding outward through the galactic gas like a slow exhalation. And if that is true, then the question of whether we are alone in the cosmos carries within it a quieter, stranger question beneath it. Not only where is life, but when? Not only across what distance must a signal travel to find us, but across what depth of time? Because the universe does not distribute its gifts evenly across history. The conditions for life did not arrive all at once, like a door swinging open on a single hinge. They accumulated. They layered. They deepened gradually, the way sediment layers at the bottom of a still lake, each year adding its thin stratum of possibility to everything that came before. And this means that the probability of encountering another civilization, another mind, another world that has followed a path even loosely similar to ours, depends not only on how common life is in space, but on how synchronized civilizations are in time. This is a dimension of the problem that is easy to overlook, and yet once you have felt its full implication, it becomes very difficult to set aside. Consider what it would require for two civilizations to make contact. Not merely to exist simultaneously in the same galaxy, though that alone is a condition of considerable improbability, but to exist simultaneously at a stage of their development at which communication across interstellar distances is even possible. To have both arrived, within a cosmically narrow window, at the technological and intellectual threshold that makes reaching outward conceivable. The universe has been producing stars and planets for billions of years. Technological civilizations, if they exist, would presumably arise and develop and perhaps decline across timescales that are, by comparison, extraordinarily brief. And so the chance that any two of them would find themselves at compatible stages of development at the same cosmic moment is a constraint that the enormity of deep time makes genuinely severe. Let yourself drift with this for a while. There is no urgency here. Only the slow expansion of a thought through the quiet of the night. Imagine a civilization that arose on a rocky world orbiting a sun not unlike ours, but 2 billion years before Earth had even formed. They would have had 2 billion years of head start. 2 billion years of accumulated knowledge, development, perhaps exploration. And if they eventually fell silent, whether through their own choices, their own failures, the ordinary attrition of entropy and time, they might have vanished from the universe's stage billions of years before the first multicellular organism had stirred in Earth's shallow ancient seas. We would have no way of knowing they had ever existed. The cosmos keeps no written record. The light they sent outward, if they sent any, would have long since dispersed beyond any instrument we could imagine building. Their radio signals, if they transmitted any, would have faded into the background hiss of the universe, indistinguishable from noise, lost in the vast and patient dark. And this is a genuinely melancholy possibility. Not catastrophic, not hopeless, but melancholy in the way that all thoughts about deep time eventually become melancholy, carrying within them the quiet recognition that existence is not permanent, that presence is not guaranteed, that the universe is large enough and old enough to have contained entire histories that left no trace we can read. The astronomer Carl Sagan once described the cosmos as a place of extraordinary violence and extraordinary beauty existing simultaneously, and this thought carries that same dual quality. The same cosmic time that makes life possible at all, the same stellar generations that built the chemical richness our biology required, also means that the history of the universe is deep enough to have contained civilizations we will never know of, minds we will never reach, stories that ended before ours began. The barrier is not only ahead of us, in the distance we must traverse to reach another world. It is also behind us, in the fathomless depth of time through which other possibilities may have already passed. But there is another face to this temporal dimension. A face that is not melancholy at all, but something closer to a quiet, grounded wonder. Because if we are living in the early era of the universe's capacity for life, if the conditions for complexity and biology and consciousness are still spreading, still deepening, still becoming more richly distributed across the galactic medium with each passing stellar generation, then the universe ahead of us may be more full of life than the universe behind us. The future of the cosmos, stretching across timescales that make our entire history feel like the first syllable of a very long sentence, may be populated with minds and worlds and conversations that we are, in some strange and tender sense, among the earliest ancestors of. That thought has a different quality. It asks something different of you. It does not invite grief for what may have been, lost in the depths of time already elapsed. It invites instead a kind of forward-facing stillness, a recognition that to exist now, in this particular moment in the universe's long unfolding, is not an accident without meaning. It is a position, a location in time as specific and as unrepeatable as a location in space. And just as no two stars occupy the same point in the galaxy, no two moments of awareness occupy the same point in the river of cosmic history. You are here, now, in this particular sliver of the universe's 14th billion year, breathing slowly in the dark, and that specificity is not nothing. It is, in fact, everything you have. Everything any mind has ever had. Let that settle into you the way warmth settles into cold hands held near a fire. Not rushing, not demanding, just arriving, slowly, at its own pace. We have been speaking of time, of the long preparation the universe required before life could arise anywhere within it, of the stellar generations that had to live and die before the raw materials of biology existed in sufficient richness. And now, moving gently forward, we can begin to feel our way toward another layer of the barrier. One that exists not in the deep past of cosmic chemical enrichment, but in the specific, local, particular conditions that a world must meet before life can take hold upon its surface and, over immense stretches of time, complexify into something capable of awareness. Because the universe being chemically ready is necessary. But it is not sufficient. A world still needs to be in the right place. Not merely the right place in the galaxy, though that matters in ways we will come to presently, but the right place around its particular star. Close enough to receive warmth. Far enough not to be scorched into barrenness. Situated within what astronomers call the habitable zone, that band of orbital distance within which liquid water can exist on a planetary surface under the right atmospheric conditions. A zone that is real and measurable and whose boundaries shift depending on the size and temperature of the star at its center. The concept of the habitable zone is one of the most quietly elegant in all of planetary science. It takes the enormous complexity of what makes a world livable and distills it, for the purposes of first approximation, into a single geometric question. How far is this world from its sun? And while the true picture is considerably more nuanced, as it always is when you press any scientific concept toward its full depth, the habitable zone gives us a framework for thinking about the distribution of potentially living worlds across the galaxy in a way that is both tractable and genuinely illuminating. Our own planet sits comfortably within the Sun's habitable zone. Not at its inner edge, where Venus orbits, a world that was perhaps once temperate and is now a place of crushing pressure and temperatures sufficient to melt lead, wrapped in clouds of sulfuric acid, a cautionary whisper about how narrow the path to habitability truly is. And not at the outer edge, where Mars drifts, a world that carries in its ancient riverbeds and dried lake floors the memory of liquid water, the memory of a warmer and wetter past, a past that ended when its magnetic field collapsed and its atmosphere was gradually stripped away by the solar wind over billions of years, leaving it cold and thin-aired and, as far as we currently know, silent. Earth, between these two quiet warnings, occupies a position that is comfortable without being guaranteed. And the word comfortable is important here, because it contains within it a kind of fragility that the word habitable does not quite convey. The Earth is not simply habitable. It is finely balanced. Its atmosphere, its oceans, its magnetic field, its distance from the Sun, its relationship with the Moon, its particular axial tilt, its carbon cycle, its plate tectonics, the long interplay of its geology and its biology in a feedback system of extraordinary intricacy. All of these factors have conspired across 4.5 billion years to maintain the conditions under which life not only arose but persisted and complexified. And it is here, in this accumulation of favorable circumstances, that the barrier acquires a new face. A face that is local rather than cosmic. Personal, almost in its specificity. Because when we ask whether another world might host life, we are not only asking whether it lies within its star's habitable zone. We are asking whether it replicates, in its own way, something like the extraordinary cascade of stabilizing conditions that Earth has maintained across geological time. Whether it has something like a magnetic field to deflect its star's more violent emissions. Whether it has something like plate tectonics to recycle carbon and regulate the long-term climate. Whether it has something like a large moon to stabilize its axial tilt and prevent the kind of chaotic rotational variations that might otherwise make surface temperatures too erratic for complex life to gain any sustained foothold. These are not exotic requirements. They are the ordinary background conditions of our own existence, things so familiar, so woven into the fabric of daily life on this planet that they are essentially invisible to us, the way water is invisible to the creatures that have never known anything else. But when you hold them up to the light of the question we are asking tonight, when you ask how common it is for a rocky world to quietly assemble all of these stabilizing conditions simultaneously over billions of years, they begin to look less like ordinary background and more like an improbable confluence. A gathering of circumstances that, taken individually, might each be plausible enough, but taken together, in the specific combination and duration that Earth has maintained them, begins to feel like something rarer than the simple arithmetic of habitable zones would initially suggest. There is a school of thought in astrobiology, serious and carefully reasoned, that takes this accumulation of conditions as its central premise. It is sometimes called the rare Earth hypothesis, a name given to it most prominently by the paleontologist Peter Ward and the astronomer Joe Kirschvink, who argued in careful and considered terms that the conditions required for complex, multicellular life are not merely the presence of liquid water and a stable temperature, but an entire architecture of planetary circumstance that may be genuinely uncommon in the galaxy. Not impossible, not unique to Earth with certainty, but uncommon in a way that matters enormously when we are thinking about how many worlds might host not just microbial life, not just the quiet chemistry of single-celled organisms in some sheltered subsurface ocean, but the kind of complex, differentiated, eventually aware life that could look upward and ask questions about the cosmos. Let this distinction rest in your awareness for a moment, because it carries real weight. The question of whether life exists elsewhere in the universe and the question of whether complex, aware life exists elsewhere are not the same question. They may not even be close to the same question. Simple life, the kind represented on Earth by bacteria and archaea, by the extraordinary microbial communities that thrive in volcanic vents at the bottom of the ocean, in the frozen brines of Antarctic ice, in the superheated acidic springs of geothermal fields, this kind of life is robust. It is ancient. It has persisted on Earth for nearly 4 billion years across conditions that have varied enormously through mass extinctions and ice ages and asteroid impacts and periods of atmospheric chemistry so different from today's that they would be lethal to most modern organisms. Simple life, once established, appears to be extraordinarily resilient. But the path from simple life to complex life, from the prokaryotic cell to the eukaryotic cell, from the single organism to the multicellular body, from the body to the nervous system, from the nervous system to the brain, from the brain to the mind that lies here quietly in the dark contemplating the size of the cosmos, that path is not guaranteed. It is not even, as far as we can tell from the single example available to us, a particularly fast or inevitable path. It took life on Earth approximately 2 billion years to make the transition from simple prokaryotic cells to the more complex eukaryotic cells that carry their genetic material enclosed in a nucleus. 2 billion years for a single cellular innovation. And the eukaryotic cell, with its internal compartments and its mitochondria and its nucleus, is the foundation upon which all complex multicellular life is built. Without it, there are no animals, no plants, no fungi, no minds. 2 billion years. Let that number move through you slowly. The universe itself is only 13.8 billion years old. The time it took life on Earth to achieve a single foundational innovation in cellular architecture is a significant fraction of the total age of the cosmos. And we do not know whether that pace was typical or anomalous. We do not know whether the eukaryotic transition is something that tends to happen on living worlds within a certain range of time, or whether it is a rare event, a narrow gateway, a threshold that most living worlds never cross. We have exactly one data point, and a single data point, however beloved, however intimately known, cannot tell us the shape of the distribution it was drawn from. This is one of the quieter frustrations woven through the whole enterprise of astrobiology, and it is worth sitting with rather than rushing past. We are trying to understand the prevalence of life in the universe using a sample size of 1. Everything we know about the origin of life, the pace of biological evolution, the conditions required for complexity to emerge, every piece of this knowledge comes from a single planet orbiting a single star in a single arm of a single galaxy among hundreds of billions. We are, in the most literal possible sense, reasoning from the inside of the only example we have. And while the logic we apply to that example is careful and rigorous and genuinely illuminating, it carries within it an irreducible uncertainty that no amount of careful reasoning can fully dissolve. There is something almost meditative about accepting that uncertainty rather than fighting it. About letting it become not a source of frustration but a kind of spaciousness. A recognition that the question is genuinely open. That the universe has not yet shown us its answer, and that the not knowing is not a failure of science but a faithful description of where we actually stand in relation to one of the deepest questions a mind can hold. And so we hold it. Gently. The way you might hold something delicate and unfamiliar in your hands in the dark, feeling its edges without being able to see its shape. The question of life's distribution across the cosmos remains open in a way that is, if you allow yourself to feel it fully, not diminishing but enlarging. Because an open question is a living question. It has not yet closed around its answer. It still contains within it every possibility, from the deeply humbling to the quietly profound. And perhaps that is where we must linger for a moment longer. In the profound. not as a word we reach for when other words feel insufficient, but as a direction, a depth. The way certain waters, when you look down into them, seem to have no bottom that the eye can find. The question of life beyond Earth is that kind of water. You can look into it for a very long time and never locate its floor. There is a concept in astronomy that does not get spoken about enough in the context of this search, and it is called the cosmic distance ladder. It is the method by which we measure how far away things are. A series of overlapping techniques, each one calibrated against the last, each one carrying us a little further out into the dark. And what is striking about this ladder, when you truly sit with it, is not how reliable it is, though it is remarkable in its reliability, but how it reveals, rung by rung, just how vast the terrain between us and anything else truly is. The nearest star to our own Sun is Proxima Centauri. It sits approximately 4.2 light-years away. That number, spoken quickly, sounds manageable. A decimal. A small thing. But a light-year is the distance light travels in an entire year, moving at nearly 300,000 kilometers every second. If you were to drive to Proxima Centauri in an average car, never stopping, never sleeping, you would be driving for roughly 45 million years. And Proxima Centauri is our nearest neighbor. It is, in the language of the cosmos, just next door. This is one of the hidden barriers. Not a wall precisely, but a distance so enormous that it functions like one. Even if life exists around Proxima Centauri, even if something breathes or thinks or wonders in the thin atmosphere of Proxima Centauri b, that planet which orbits within its star's habitable zone, we could not simply reach out and touch it. We could not send a message and receive a reply within a human lifetime. The gap between us is measured not in miles but in years of light, and light is the fastest thing the universe allows. There is something almost sorrowful about this, if you let yourself feel it without resistance. We live in a universe that may be full of voices, and yet the acoustics of space-time mean that most of those voices will never reach us, at least not in any form we would recognize as conversation. The signals, if they exist, are attenuated by distance, scattered by the interstellar medium, the thin but persistent soup of gas and dust and magnetic fields that fills the space between stars. A radio transmission sent from a civilization 10,000 light-years away would arrive at our antenna, if it arrived at all, so faint that distinguishing it from the background noise of the cosmos becomes an act of extraordinary technical patience. And yet we have listened. We have been listening, in a formal and organized way, since 1960, when Frank Drake pointed a radio telescope at the stars Tau Ceti and Epsilon Eridani and tuned it to a frequency he thought a technologically curious civilization might use. He heard nothing of certain origin, but he kept listening, and the projects that followed him kept listening. Thousands of hours of observation, millions of radio frequencies scanned, the sky swept again and again with instruments of increasing sensitivity. The silence has been, so far, the only reply. There was one exception, or what felt briefly like one. In 1977, an astronomer named Jerry Emmon, working at the Big Ear Radio Observatory in Ohio, detected a signal so anomalous, so striking in its structure, that he circled it on the printout with a red pen and wrote beside it a single word. Wow. The signal lasted 72 seconds, which was exactly as long as the telescope's observation window allowed. It had the characteristics that researchers had theorized an extraterrestrial transmission might possess. It was narrow in frequency. It was strong. It came from the direction of the constellation Sagittarius. And then it was gone. It has never been detected again, despite many attempts to find it at the same coordinates, with the same equipment, in the same frequency range. The WOW signal remains unexplained. Not proven to be alien. Not proven to be anything, precisely. A single anomaly, sitting at the edge of the known, resistant to clean resolution. It is tempting to want to make it mean something definitive. The mind reaches for closure the way the hand reaches for a light switch in a dark room. But the wow signal, like so much in this domain, resists that reaching. It simply was. A pattern in the noise that we do not fully understand, a moment when the universe seemed to say something and then fell silent again before we could be sure we had heard it correctly. And this, too, is part of the hidden barrier. Not just the physical distance, not just the faintness of signals crossing the void, but the interpretive gap. The difficulty of knowing, even when something reaches us, whether it carries meaning or is simply the cosmos doing what it does, producing patterns that feel, to pattern-hungry minds, like language, when language is not there. The human mind is, before almost anything else, a pattern-finding instrument. It evolved in an environment where recognizing patterns quickly meant the difference between eating and being eaten, between shelter found and shelter missed. We see faces in clouds. We hear rhythm in rainfall. We find meaning in the arrangement of stars, which is why every culture that has ever existed beneath an open sky has drawn pictures across them, connected the dots, named the shapes, built stories around the configurations. Orion, the bear, the scorpion, the Southern Cross. The stars themselves did not arrange into these forms. We arranged them. We reached across the distances with our imagination and made the random feel intentional. This is not a flaw. It is, in many ways, the engine of everything we have built. The capacity to detect signal within noise, to find a thread of meaning running through a complex and indifferent environment, is the same capacity that built telescopes and wrote equations and conceived of the search for extraterrestrial intelligence in the first place. But it also means that we must hold our interpretations gently, especially when the subject is one as charged and as hope-laden as the possibility of contact. The mind wants to hear a voice in the static, and so we must develop the patience and the discipline to ask whether what we are hearing is truly a voice, or whether we have simply brought our longing to the noise and given it a shape it did not originally possess. The wow signal sits at that boundary, as do certain anomalies in stellar light curves, certain unexplained radio transients, certain structures in data that researchers flag with cautious language and careful caveats because the alternative, to declare without sufficient evidence that contact has been made, would be to mistake the map of our desire for the territory of the real. And science, at its most honest, is a practice of resisting exactly that mistake. Of sitting with the data as it is, not as we wish it to be. There is a kind of discipline required here that resembles, in its texture, something closer to contemplation than to calculation. A willingness to remain in uncertainty without filling it prematurely with conclusion. The great astronomers and astrobiologists working on these questions have, many of them, spent entire careers building instruments, designing experiments, refining methods, all in service of a question that has not yet yielded a definitive answer. There is something deeply human about that dedication. Something that speaks to a capacity we have, when we are at our best, for sustained and patient wonder. Carl Sagan, who perhaps more than any other figure in the 20th century made the search for cosmic life feel like a legitimate and even urgent pursuit, wrote that somewhere, something incredible is waiting to be known. He did not say it had already been found. He did not say the answer was close or that the wait would be short. He located the incredible in the waiting itself, in the posture of openness toward a universe still being understood. And the universe is still being understood, at a pace and scale that would have seemed impossible to scientists working even 50 years ago. The James Webb Space Telescope, which began returning its earliest science observations in 2022, has already begun to complicate and enrich our picture of how galaxies form, how early stars ignited, what the chemical compositions of planetary atmospheres might look like from across dozens of light years. It carries an instrument suite capable of detecting, under the right conditions, the spectral signatures of molecules in the air of worlds orbiting other suns. Molecules like water vapor, carbon dioxide, methane, and in the most anticipated scenario, combinations of gases that would be chemically unstable in the absence of continuous biological production. Oxygen paired with methane. The atmosphere quietly advertising the presence of something alive within it. We have not found that signature yet. But we are, for the first time in human history, holding an instrument in space that is technically capable of recognizing it. We are looking, and the looking itself marks a threshold. A moment in the long story of this species when the question moved from purely philosophical to genuinely empirical. When we stopped simply wondering and began, however haltingly, to check. What we will find is still unknown. The atmospheres of exoplanets are difficult to characterize. The signals are faint. The interpretations are contested. A planet must pass directly between its star and our telescope for us to read the light that filters through its atmosphere, and not every planet orbits at the angle required. We are dependent on geometry, on timing, on the alignment of distant worlds in ways we cannot control, only await. And so we await. The telescopes gather light, the computers process it, the scientists examine the data with the careful eyes of people who know that the history of this search is strewn with false signals and misread patterns, and who proceed anyway because the alternative, which is not to look, would be its own kind of surrender. There are those who argue that the silence itself, the long and unbroken quiet of the cosmos in response to our listening, carries meaning. That an absence of detected signals is not merely the absence of evidence but a clue, a shape made from what is not there, pointing toward some conclusion about the rarity of technological civilizations, or the brevity of their existence, or the nature of the barriers that prevent them from being heard across the void. This line of thinking has a name. It is called the Fermi paradox, after the physicist Enrico Fermi, who, during a casual lunch conversation in 1950, asked a question so simple and so devastating in its implications that it has occupied serious scientific thought ever since. The question, distilled to its essence, was this: if the universe is as old and as large as we believe it to be, and if the conditions for life are not extraordinarily rare, then where is everybody? Not as a rhetorical flourish, as a genuine inquiry into an apparent contradiction. The universe has had billions of years to produce technological civilizations. Some of those civilizations, if they exist, should have had time enough to spread across the galaxy, or at least to make their presence known in ways we could detect. And yet the sky is quiet. The instruments return nothing certain. The silence persists. There are many proposed resolutions to this paradox, and they range across a spectrum from the hopeful to the deeply unsettling. One possibility is that we are simply not listening in the right way, or at the right frequencies, or with sufficient sensitivity. That the signals are there, woven into the electromagnetic fabric of the cosmos, and we have not yet built the instruments precise enough or patient enough to find them. This resolution requires no dark conclusion. It asks only for more time and better tools, both of which seem, in principle, attainable. Another possibility is that technological civilizations tend to be short-lived. That the same intelligence which allows a species to develop radio telescopes and nuclear physics and spacefaring ambitions also carries within it the seeds of its own undoing. That the window during which a civilization is both capable of broadcasting its presence and willing to do so is, measured against cosmic time, vanishingly narrow. A few centuries, perhaps. A few thousand years at most. And then silence, for one reason or another. This possibility sits heavier than the first. It carries within it an implication about our own trajectory that is not comfortable to hold in the mind, especially in the quiet hours of a night already given over to reflection. There is a related idea, one that researchers sometimes call the Great Filter. The notion that somewhere along the path from simple chemistry to spacefaring civilization, there exists a step so difficult, so unlikely, so demanding of precisely the right conditions in precisely the right sequence, that almost nothing makes it through. The great filter is either behind us or ahead of us, and the difference between those two positions is, in its implications, staggering. If the filter is behind us, if the great improbability was the emergence of complex life, or of the eukaryotic cell, or of multicellular organisms, or of something else we have already accomplished, then our existence here is a kind of miracle, and the silence of the cosmos reflects the extraordinary difficulty of reaching this point. We are rare. We are perhaps alone. And the future, filtered though it was, remains open. But if the filter is ahead of us, if the difficult step is one we have not yet faced, then the silence of the cosmos becomes a warning rather than a comfort. It suggests that something awaits every civilization that reaches our level of development, something that stops the clock, something that explains why the galaxy is not filled with signals and probes and the accumulated noise of 1,000 technological species broadcasting their existence into the dark. This interpretation does not tell us what the filter is, only that it may be waiting. Only that the quiet of the sky might be, if you allow the thought to land fully, a kind of testimony. These are the thoughts that come in the deep hours, when the mind has slowed enough to let them in. They are not comfortable thoughts, but they are honest ones. And there is a quality to honest discomfort that is different from despair. It has a clarity to it, a kind of seriousness that feels, in its own way, like respect. Respect for the scale of what we are trying to understand. Respect for the genuine uncertainty of our situation. Respect for the fact that we are a species young enough to still not know its own fate, and old enough to have learned to ask the question. What we do with the silence is, in some ways, a reflection of who we are. Whether we read it as emptiness or as space. Whether it diminishes our sense of significance or deepens our sense of responsibility. Whether the apparent solitude of our world in this vast and ancient universe makes what happens here feel meaningless, or makes it feel, on the contrary, extraordinarily precious. A single candle in a very large and very dark room is not diminished by the darkness around it. It is, if anything, made more visible, more remarkable, more worth protecting. The stars do not know we are here. They burn without awareness, without intention, without any reference to the small warm planet circling one of their number where creatures developed, over billions of years, the capacity to look back at them and wonder. That wondering is not nothing. It may be, in fact, one of the rarest and most fragile things the universe has yet produced within itself. A way of knowing that it exists. There is a phrase that the philosopher Thomas Nagel used in a different context, but which carries a strange and luminous relevance here. He wrote about the difficulty of understanding what it is like to be something other than what you are. His example was a bat, navigating the dark by sound, experiencing a world so different from our own that our imagination, however generous, cannot fully close the gap. We can describe echolocation in precise physical terms. We can map the frequencies, trace the neural pathways, model the spatial picture that emerges from reflected sound. And yet something escapes the description. Something about the texture of that experience, the quality of what it is like from the inside, remains beyond our reach. Now extend that thought outward, past the bat, past the animal kingdom, past the boundaries of this planet and its particular evolutionary history. If life exists elsewhere, if it emerged in the ammonia clouds of a gas giant, or in the liquid methane seas of a moon like Titan, or in the superheated waters surrounding a hydrothermal vent on an ocean floor beneath kilometers of ice, then whatever experience that life might have, if it has experience at all, would be separated from ours not merely by geography but by the entire history of its becoming. Every adaptation, every chemical pathway, every sensory apparatus shaped by a completely different set of pressures over a completely different span of time. The gap between us and such a life form would make the gap between a human and a bat feel, by comparison, almost intimate. This is one of the hidden barriers that rarely appears in the technical literature, but which sits quietly beneath every conversation about contact. Even if we found evidence of life, even if the spectral signature of a distant atmosphere confirmed beyond reasonable doubt that something biological was producing gases in the air of another world, the distance between that confirmation and any genuine understanding of what that life is would remain enormous. We would know that it existed. We would know almost nothing of what it meant to be it. The knowing and the understanding are not the same threshold, and crossing the first does not automatically carry you to the second. Saturn's moon Titan drifts through its slow orbit in a way that has fascinated planetary scientists for decades. Its atmosphere is thick and orange and rich with organic chemistry. It has lakes and rivers and rain, but not of water, of liquid methane. The cycle of evaporation and precipitation that shapes its weather is, in structure, not entirely unlike the water cycle on Earth, but the medium is so different, the temperature so extreme, around -179 degrees Celsius, that the chemistry operating within it belongs to a register we associate not with life but with industrial solvents. And yet there are researchers who take seriously the possibility that some form of chemistry complex enough to be called life might operate there. Not life as we know it. Not life built around liquid water and carbon chemistry in the temperature range we inhabit. Something else. Something that would require us to expand our definition before we could even recognize it as belonging to the category we were searching for. This question of definition is itself a barrier, subtle but significant. We search for life, but our instruments are calibrated to find life that resembles what we already know. The biosignatures we look for in exoplanet atmospheres, oxygen, methane, water vapor, are the signatures of Earth-like biology. If life on another world operates by entirely different chemistry, produces entirely different byproducts, leaves an entirely different mark on its environment, we might look directly at the evidence and not recognize it. We might classify it as geology, as atmospheric chemistry, as something interesting but not biological, because biological, to the instruments we have built and the frameworks we carry, means something specific, means something that looks, at least in its broadest outlines, like us. There is a humility required by this recognition that goes deeper than the usual scientific humility of acknowledging what we do not yet know. It is a humility about the shape of our ignorance itself. Not merely that we lack answers, but that we may lack the conceptual vocabulary to formulate the right questions. That the map of our understanding has edges we cannot see because we are standing at the center of it, and the edges are where they always are, just beyond where the known terrain runs out. Astrobiologists call this the problem of a sample size of 1. Every piece of biology we have ever studied, from the simplest archaean living in a volcanic hot spring to the most complex neural architecture of the human brain, is part of a single lineage, a single experiment. Life on Earth, however diverse it appears from the inside, is in a deeper sense one thing. It shares a genetic code. It uses the same 20 amino acids. It stores information in the same molecule. We have never encountered a second genesis, a second independent origin of life with its own solutions to the problems of metabolism and replication and adaptation. And so when we try to reason about life in general, about what life does and what it requires and what it might look like elsewhere, we are reasoning from a single data point, constructing a general theory from one example, one case study, one particular throw of the cosmic dice. And that singularity warps everything. It warps the way we define life itself, because every definition we have ever proposed has been quietly shaped by the only life we know. When scientists say that life requires liquid water, They are not stating a universal law derived from first principles. They are observing that every organism they have ever encountered requires liquid water, and then, almost inevitably, extrapolating outward. It is a reasonable extrapolation. Water is a remarkable solvent. It is abundant across the cosmos. It has properties that seem almost tailored to the chemistry of self-replication and energy exchange. But remarkable is not the same as necessary. Abundant is not the same as irreplaceable. And the history of science is a long record of reasonable extrapolations that turned out to be the walls of a room we did not know we were standing in. Consider the question of carbon. Life as we know it is built on carbon chemistry, and for good reasons. Carbon forms more molecular compounds than any other element. It bonds with itself and with other atoms in ways that produce structures of astonishing complexity, the long chains and rings and branching architectures that underlie proteins and nucleic acids and the membranes of cells. Carbon is, in the language of chemistry, promiscuous in the best possible sense. It connects. It combines. It enables the kind of molecular diversity that seems to be a prerequisite for the kind of information storage that seems to be a prerequisite for the kind of adaptation that we recognize as life. And yet silicon exists. Silicon, which sits just below carbon on the periodic table and shares some of its bonding properties. Silicon-based chemistry is less flexible, less diverse, less soluble in water. But we have never tested it in the conditions of an alien world with an alien chemistry and billions of years of evolutionary pressure. We have never watched silicon explore its own possibilities the way carbon has explored its. We have said it is less promising, and it is, by the measures we apply, which are measures built from carbon's example. This is the recursion that haunts the search for life. We look for what we know. We look for it where we expect to find it. And we build our instruments to detect the signatures we already understand, because those are the signatures we are capable of designing instruments to detect. The James Webb Space Telescope, extraordinary as it is, searches for biosignatures in the atmospheres of distant planets by looking for chemical imbalances, the presence of gases that should not coexist without some ongoing process to maintain them. Oxygen and methane together. Ozone. Water vapor. These are signatures because life on Earth produces them, because our biosphere has spent billions of years rewriting the chemistry of our atmosphere in ways that are, from a distance, unmistakable. But that detectability is a consequence of the particular chemistry of life as we know it. A life that does not produce oxygen would leave a different signature. A life that processes energy through pathways we have not imagined might alter its environment in ways our instruments would record as noise, as background, as nothing. There is a thought experiment that astrobiologists return to sometimes, not as a method, but as a meditation. Imagine that you are an alien intelligence, and you are looking at Earth from a distance of 40 light years, which is the distance of some of the exoplanets we study most carefully. You have technology comparable to our own, perhaps slightly more advanced. You are searching for life. You find our planet. You analyze the spectrum of sunlight filtered through our atmosphere. You find oxygen. You find methane. You find the faint infrared signature of a warm, wet world. And then, if you are lucky and your instruments are sensitive enough, you find something stranger. A very faint, very specific, very regular series of radio emissions. Not natural. Not random. Structured in a way that only intention could produce. Do you recognize what you are seeing? Do you have a framework for understanding that those radio waves represent minds, cities, a civilization asking the same question you are asking, wondering whether it is alone? Or does the signal fall into a category your science has not yet invented, a phenomenon you observe, record, and eventually set aside because it does not fit anything you know how to interpret? That thought experiment cuts in both directions. It suggests that we might already be detectable to someone watching. And it suggests that something, somewhere, might already be transmitting, might have been transmitting for longer than our civilization has existed, in a medium or a frequency or a language that our instruments do not yet know how to hear. The universe is not obligated to communicate in the channels we have opened. It does not owe us a signal in the radio spectrum, or in visible light, or in any wavelength our technology has learned to collect. The history of astronomy is, in one reading, a history of opening new eyes, of building instruments sensitive to radiation we could not previously perceive, and discovering every time that the universe had been doing things there, in that newly visible domain, all along. X-ray astronomy revealed a cosmos of violence and energy invisible to optical telescopes. Radio astronomy revealed the cosmic microwave background, the faint afterglow of the beginning of everything, murmuring in every direction at once. Infrared astronomy revealed the warmth of stellar nurseries hidden inside clouds of dust. Each new eye showed us a universe that had not changed, but that we were seeing, finally, more completely. And we are still opening eyes. Still building instruments that will show us things we currently cannot imagine seeing, and every expansion of our perceptual range carries within it the quiet possibility that somewhere in the newly visible domain, something is already there, already present, already doing whatever it does in the frequencies we had not yet learned to listen to. And so the search continues, not as a single organized effort with a clear methodology and a shared definition of success, but as something more diffuse and more human than that. It continues in the analysis of ancient meteorites, those travelers from the early solar system that carry within their mineral structures a record of chemistry from before the Earth existed. It continues in the study of extremophiles, the organisms that live in places we once believed were simply incompatible with life, in the superheated water of deep ocean hydrothermal vents, in the hypersaline lakes of Antarctica where the ice itself is threaded with brine channels teeming with microbial communities, in the dry valleys where ultraviolet radiation strips the surface bare and life retreats into the interior of rocks, surviving in the thin layer of moisture and light that penetrates just beneath the surface, finding a way because life, in our experience, finds a way. Each extremophile is a data point. Each one slightly widens the circle of what is possible. Each one quietly repositions the boundaries of the habitable. There is something almost devotional about this work. The astrobiologist who spends years studying the chemistry of hydrothermal vents, the planetary scientist who models the subsurface ocean of Europa with painstaking computational care, the radio astronomer who sifts through petabytes of signal data looking for a pattern that stands apart from the static of the cosmos. These are not people motivated only by professional ambition or scientific curiosity in its narrow sense. They are people sitting with a question that is too large to answer in a lifetime, and they are sitting with it anyway. They have chosen to orient their intellectual lives around a mystery that may not resolve on any human timescale, and there is something in that choice that feels less like science in the conventional sense and more like a practice, a sustained attention directed at something vast and uncertain and deeply important. The question they are sitting with is not merely whether life exists elsewhere. That question, as profound as it is in some sense the smaller one. Beneath it lies something more fundamental. It is the question of whether the emergence of life is a rare accident or a deep tendency, whether the universe is the kind of place that makes life the way it makes stars, through processes so general and so robust that given enough time and the right conditions they happen more or less inevitably, or whether life is a singular improbability, a thread of extraordinary fortune woven through a cosmos that is mostly and permanently lifeless. Those two possibilities lead to universes that feel entirely different from the inside. In the first, even if we never make contact, even if the distances remain insurmountable and the silence is permanent, we are part of a living universe, a cosmos threaded with biology in the way it is threaded with hydrogen and carbon and the slow nuclear fires of stars. In the second, we are something stranger and more precarious than that. We are the accident that knows it is an accident, the improbability that has become aware of its own improbability, looking out at a vast machinery of matter and energy and time that produced us once and perhaps never again. Both of those possibilities are vertiginous in their own way. The first suggests a companionship we cannot yet reach. The second suggests a solitude so profound it borders on the incomprehensible. And we do not know which one is true. We are standing between them in the dark, holding instruments that can detect the presence of oxygen in the atmosphere of a planet 40 light-years away, and we are waiting. Europa drifts through the Jovian night, its icy surface cracked into patterns that geologists of the solar system describe in terms borrowed from cartography and architecture. Ridges, bands, chaos terrain. Beneath that surface, separated from the vacuum of space by a shell of ice that may be anywhere from a few kilometers to 30 kilometers thick, a liquid ocean moves in response to the tidal flexing of Jupiter's gravity. That flexing generates heat. That heat keeps the water liquid. That liquid water sits in contact with a rocky seafloor, and wherever liquid water meets rock in the presence of chemical gradients and thermal energy, we have seen life find purchase. We have not visited Europa's ocean. We have inferred it from the magnetic signatures and surface features and spectral data gathered by spacecraft that flew past or orbited from a distance. But the inference is robust. The ocean is almost certainly there, and it has been there for perhaps as long as the solar system itself, billions of years of liquid water in the dark, beneath the ice, warmed by the gravity of a gas giant, far from the sun, in a place we would not have thought to look if we had not learned to look in unexpected places. And Europa is only one such place. Enceladus, the small bright moon of Saturn, erupts geysers of water vapor and ice particles from its southern pole, venting material from a subsurface ocean directly into space, where passing spacecraft have flown through the plumes and tasted them, finding organic molecules, finding molecular hydrogen, finding the chemical signatures of hydrothermal activity on the ocean floor far below. The geysers of Enceladus are, in a sense, an invitation. The ocean is offering itself up for analysis without requiring us to drill through kilometers of ice or descend into darkness. It is sending its chemistry outward into space, and we have been there to receive it, and what we have received has been, to put it carefully and precisely, consistent with habitability. Not proof of life. Not even a strong suggestion of life. But consistent with the conditions under which life, by our best understanding, could exist and persist. That careful language matters. Science moves in it the way a careful traveler moves through uncertain terrain, placing each foot deliberately, testing the ground before committing weight. Consistent with habitability is not the same as inhabited. The presence of organic molecules is not the presence of organisms. Organic chemistry happens everywhere in the cosmos, in the clouds between stars, in the comas of comets, in the dark chemistry of carbonaceous meteorites. The universe makes organic molecules with a kind of casual abundance that would have astonished the chemists of earlier centuries, who associated carbon chemistry with the presence of life, who believed that the molecules of living things could only be produced by living things, a belief so deeply held it had a name, vitalism, and a history of resistance even as evidence against it accumulated. We know now that the cosmos does not share that boundary. It makes the building blocks without the building. It assembles the precursors without assembling the thing itself, or at least, that is what we observe everywhere we have looked except here, on the only world where we know the final step was taken. Titan drifts through the outer solar system in a haze of orange nitrogen and complex hydrocarbons, a world so strange and so richly chemical that planetary scientists describe it sometimes with a kind of barely contained wonder. It has a thick atmosphere, denser at the surface than Earth's, layered with organic compounds that rain down continuously onto a landscape of water ice bedrock and hydrocarbon lakes. Those lakes are not water. They are liquid methane and ethane, pooled in low-lying basins near the poles, dark and still under a butterscotch sky. Life as we know it could not survive in them. The temperatures are nearly 200 degrees below 0 Celsius, cold enough to freeze any biochemistry we understand into stillness. But some theorists have proposed, carefully and with appropriate uncertainty, that a different kind of life might be possible there. Not water-based life. Not life using the liquid of our biosphere. But life using liquid methane as its solvent, with a biochemistry so different from ours that we would not recognize its signatures with instruments designed to find us. We have no evidence for such life. We have only the theoretical possibility, the observation that Titan's chemistry is extraordinarily complex, and the knowledge that complexity, given time, has a way of finding configurations we did not predict. The Dragonfly mission, a rotorcraft lander designed to fly across Titan's surface and sample its chemistry in multiple locations, is intended to reach Titan in the coming years and begin answering some of these questions, or at least asking them more precisely than we can from a distance. It will not resolve the question of life on Titan, but it will deepen our understanding of what is chemically possible in a world utterly unlike our own, and every deepening of that understanding is a small expansion of the map, another few kilometers of known terrain before the edge. Mars hangs in our imagination with a particular weight, closer than the icy moons of the outer planets, more accessible, more studied, more personally present in the human relationship with the night sky. It is the world we have visited most thoroughly with our machines, the world where we have driven rovers across ancient lake beds and drilled into sedimentary rock laid down when Mars was young and warm and wet. The evidence for ancient liquid water on Mars is not ambiguous. It is written in the mineralogy of the surface, in the river valleys and delta formations, and the chemical signatures of minerals that only form in the presence of sustained liquid water. Mars had water. Mars had, for a period measured in hundreds of millions of years, conditions that would have been, by our best measures, habitable. Whether anything lived in those conditions, whether the chemistry of those ancient lakes and rivers ever crossed the threshold from complex to living, we do not yet know. The samples collected by the Perseverance rover await return to Earth laboratories where they will be analyzed with instruments of a precision and sensitivity that no spacecraft could carry, and those analyses may tell us something, or they may deepen the silence. Because silence is also data. The absence of biosignatures, if confirmed thoroughly enough, would tell us something real and important about the conditions under which life emerges. It would suggest that habitability is not sufficient, that liquid water and organic chemistry and energy gradients are necessary but not enough, that something else is required, some additional condition or some particular sequence of events or some threshold of complexity that Mars approached and did not cross. And that something else is the deepest mystery, the part of the question we have not yet learned to ask with precision, because we do not know what it is. We have a name for it, abiogenesis, the origin of life from non-living chemistry, the moment or the process or the threshold at which matter began to do something we recognize as alive. But the name is not an explanation. It is a placeholder, a word-shaped space where understanding has not yet arrived. We know that life on Earth appeared relatively quickly by geological standards, within a few 100 million years of the planet's formation, which suggests either that the transition from chemistry to biology is not extraordinarily difficult given the right conditions, or that we are the result of an early accident that happened to persist, and that the apparent speed of life's emergence on Earth tells us nothing reliable about how often it happens elsewhere. Both interpretations are consistent with what we observe. Neither can be ruled out, and so the placeholder remains, hovering in the center of our understanding, a gap that is also, in a quieter sense, an invitation. The origin of life is studied now with a rigor and a sophistication that would have been unimaginable a generation ago. Laboratories recreate the chemistry of early Earth, the warm little ponds Darwin imagined, the hydrothermal vent systems where alkaline water meets acidic ocean in a natural proton gradient that some researchers believe was the original energy source for the first metabolic processes. RNA molecules have been synthesized under plausible prebiotic conditions. Lipid membranes have been shown to form spontaneously in water, to encapsulate molecules, to grow and divide in ways that echo, distantly and incompletely, the behavior of cells. Each experiment is a small proof of possibility. Each one demonstrates that some step in the sequence from chemistry to life is not forbidden, is not miraculous, is in principle achievable by matter following ordinary physical and chemical laws. And yet the full sequence remains undemonstrated. The gap between the most sophisticated prebiotic chemistry we can produce in a laboratory and the simplest living cell we know of remains enormous, populated by steps we have not yet mapped, transitions we have not yet understood. Life did not leave a record of its own origin. It arrived, and then it immediately began changing everything, including the conditions under which it had emerged. There is a particular kind of silence in that gap. Not the silence of empty space, which is immense and cold and indifferent in the way that physical things are indifferent. This is a different silence, the silence of a process that happened once, that we cannot replay, that left no witnesses and no transcript. We are trying to reconstruct the first sentence ever spoken in a language that no longer exists, from fragments recovered by archaeologists who were not there and whose tools were designed for other purposes. And we are doing it with the knowledge that if we could reconstruct it, if we could understand the sequence of events that led from simple chemistry to the first replicating molecule to the first cell, we would have something more than a scientific result. We would have a kind of key, a way of estimating how common that transition is, how many of the habitable worlds scattered across the galaxy have crossed that same threshold, how full or how empty the universe truly is. The exoplanet surveys of the past 2 decades have given us a new sense of the scale of the opportunity. Before the Kepler Space Telescope launched in 2009, we knew of a few hundred planets beyond our solar system, most of them gas giants detected by the slight wobble they induced in their parent stars, nothing like Earth, nothing that suggested a familiar kind of habitability. Kepler changed that. Over its 9 years of operation, it confirmed the existence of more than 2,500 exoplanets and identified thousands more candidates, and among them, orbiting in the habitable zones of their stars at distances where liquid water could persist on a rocky surface, were worlds of a size and a type we recognized. Not Earths confirmed as inhabited. Not even Earths confirmed as Earth-like in their chemistry or their geology or their history. But worlds of the right size, in the right place, around stars stable enough to allow for the slow work of evolution. The statistical inference from Kepler's sample suggested that small rocky planets in habitable zones are not rare. They may orbit a significant fraction of all Sun-like stars, and Sun-like stars are themselves not rare, numbering in the billions in our galaxy alone. The arithmetic is familiar by now, repeated often enough that it has acquired a kind of meditative quality, a mantra of scale that the mind accepts but cannot fully inhabit. Hundreds of billions of stars in the Milky Way. A significant fraction with rocky planets in habitable zones. Hundreds of millions of potentially habitable worlds in our galaxy alone. Hundreds of billions of galaxies in the observable universe, each with its own hundreds of billions of stars, each with its own statistical fraction of worlds where the conditions for life as we understand it might exist. The numbers accumulate into something that does not feel like arithmetic anymore. They feel like an argument, a pressure, a quiet insistence that the universe is not the kind of place that makes habitable worlds by the hundreds of millions and then fills only one of them. And yet the silence persists. The sky does not answer. The signals we have sent have received no reply, or none we have recognized, and the signals we have searched for have not materialized into anything confirmed and unambiguous, and the tension between the arithmetic and the silence is the tension that defines this entire search, this entire vigil we have been keeping since we first turned instruments toward the sky and asked, with the particular longing of a species that has always told stories about the stars, whether anyone else was out there, telling stories too. The Fermi paradox, as it is called, is not really a paradox in the strict logical sense. It is a dissonance, a tension between an expectation and an observation, between what the numbers seem to suggest should be true and what the silence seems to be telling us. Enrico Fermi asked the question at lunch in 1950, casually, the way profound questions sometimes arrive, not in formal settings but in the middle of ordinary life. If the universe is as old as it is, and as large as it is, and if the emergence of intelligent life is not extraordinarily improbable, then civilizations should have had time not merely to arise but to spread, to send signals, to fill the galaxy with the evidence of their existence. And yet, Fermi observed, we see nothing. Where is everybody? The question was simple. The answers have multiplied for decades without converging, each one carrying its own implications, its own vision of what the universe is like and what our place in it might mean. Perhaps the emergence of intelligent life is far rarer than the numbers suggest, rare enough that we are the only example in our galaxy, possibly in the observable universe. Perhaps the step from simple life to complex multicellular life is the great filter, the improbable transition that most inhabited worlds never make. Perhaps it is the step from complex life to intelligence, or from intelligence to technology, or from technology to a civilization stable enough to persist for the timescales required to make contact across interstellar distances. Perhaps the filter is behind us, in our past, in the extraordinary sequence of contingencies that led from the first cell to the first mind to the first radio telescope. And if it is behind us, then perhaps we are something extraordinary in a universe that is mostly silent, mostly dark, mostly composed of matter that has never once arranged itself into something that looks up and wonders. Or perhaps the filter is ahead. Perhaps civilizations arise with some regularity and then, for reasons we are only beginning to understand in ourselves, do not persist. Perhaps the same intelligence that allows a species to develop technology also generates the instabilities that threaten it, the capacity for conflict, for short-term thinking, for the alteration of planetary systems in ways that cannot be sustained. Perhaps the silence is a kind of warning written in the absence of voices, a statistical regularity in the fate of civilizations that we have not yet learned to read because we are still early enough in our own story that the ending is not written. These possibilities do not feel abstract when you hold them quietly in the dark. They feel personal. They feel like questions addressed not to science in general but to us specifically, to this particular civilization at this particular moment, aware enough to ask the question and uncertain enough about the answer that the asking still matters. And yet there is something in the asking itself that feels like more than anxiety. There is something in the sustained attention we have given to this question, in the careers devoted to it and the instruments built for it and the long vigil of listening that continues tonight as you rest, that feels like a kind of reaching. Not desperate reaching, not the reaching of a species that cannot bear its solitude, but the quieter reaching of a mind that has become large enough to wonder whether it is alone, and has decided that the wondering is worth sustaining regardless of what the answer turns out to be. The universe is under no obligation to provide us with company. It is under no obligation to have arranged its chemistry and its physics in ways that produce minds more than once. But we have decided to look anyway, and there is something in that decision that is, in its own way, one of the most remarkable things our species has ever done. The telescopes are still turning. The data is still flowing. Somewhere in an archive, in a dataset not yet fully analyzed, in a frequency not yet carefully examined, in a spectral signature from a distant atmosphere that has not yet been interpreted, there may be something waiting. Not certainly, not probably, in any rigorous statistical sense, but possibly. And possibility, when it is attached to a question this large, is not a small thing. It is the thing that keeps the instruments running through the night, that keeps the researchers returning to their data, that keeps the question alive across generations of scientists who each add their small increment to an understanding that no single lifetime could complete. You are part of a universe that is 13.8 billion years old. You are made of atoms forged in stars that lived and died before our sun existed. You are the latest expression of a process that began in conditions we can barely model and has been complexifying ever since, without plan, without guarantee, driven by nothing more or less than the laws of physics playing out across time. And tonight, as you drift toward sleep, those same laws are playing out on 100 million other worlds, in conditions we have not visited and through processes we have not fully imagined, in a silence that may be empty or may be full of something we have not yet learned to hear. The universe is not finished. Neither is the listening. And somewhere in the dark between the stars, something may be listening back.